Getting the best from Chemistry Explained needs you to participate. So write notes, complete tasks on paper or tablet. Pause and control the pace at which the lesson goes. Crucially, complete the tasks when prompted. That means pausing the lesson, taking your time, thinking the problem through. Only when you're ready, continue. Correct your work before moving on to the next slide. Naming and representing organic formulae. So let's start with the alkane homologous series. So homologous series being molecules with a general formula and similar chemical properties. So let's look at the alkanes, and I'd like you to pause the video and fill in the names of the first four and the formulae for pentane and hexane, and then complete the molecular formulae for the right hand set, and finally the general formula. So this is all required knowledge in OCR A. So pause the video and complete that task, please. Okay, so let's just share the answers with you. So methane, ethane, propane, butane, so that will form the stem based on those numbers of carbon atoms. Pentane with 5 carbons, hexane indicates 6 carbons, heptane indicates 7 carbons, octane 8, nonane 9, decane 10. You are expected to know those names and the relationship with numbers of carbons. So the general formula for an alkane, if you look at all of those, hopefully you have filled in CnH2n plus 2. If not, check that it works. For instance, 10 carbons, 2 times 10 is 20, plus 2 makes 22. And as well as having a general formula, then the alkanes all differ in sequence by CH2. So how might you represent an alkane such as butane? Well, there's 3 ways of representing the structure of butane, and you are required to be able to do all 3 and to be able to identify the name of that type of structure. So we start off with a structural formula. Pause the video and write a structural formula for butane. Okay, so there's 2 ways that formula can be written. We can have, I'll use my laser, CH3, CH2, CH2, CH3, or the pair of CH2s in the middle of the carbon chain can be abbreviated as like so, CH2 inside a bracket twice. Obviously not particularly useful with butane, but were the molecule much longer, then that's a very useful way of representing the structural formula. However, there are 2 other types of formula that you need to know about: a displayed formula and a skeletal formula. Could you represent butane as a displayed formula and then as a skeletal? Pause the video and do that now. Okay, so when we look at the displayed formula, what we're doing is showing all the atoms and all the bonds and the way that they are arranged. So a displayed formula shows all the atoms and all the bonds and the arrangement of them. A skeletal formula, on the other hand, does not show carbon atoms, does not show hydrogen atoms, but does show carbon-carbon bonds and any other types of atom. So we don't have carbon atoms, we don't have hydrogen atoms, we don't have carbon-hydrogen bonds, but we do have carbon-carbon bonds and any other atoms and the bonds that arise from them. So butane as a skeletal would be like so. So we've got one carbon here, the second carbon, the third and the fourth. So a bond between the first and the second carbon, between the second and the third, and a bond between the third and the fourth carbon. There are no carbon atoms shown. There are no hydrogen atoms shown. There are no carbon-hydrogen bonds. We're left, if we compare the displayed formula to the skeletal, we take out the hydrogen atoms, we take out the carbon atoms, we take out the carbon-hydrogen bonds. We're only left with 1, 2, 3 carbon-carbon bonds. So that is the method for a skeletal formula. So based on the discussion of the structures of butane, or the ways of representing butane, could you represent pentane in 4 different ways? Pause the video and complete that task. Okay, so let's check your answers against mine. So one can represent butane as a structural formula, or one can abbreviate it so that the three CH2 groups just within one bracket. So those are both structural formulae. You need to know that is a structural formula. We look at the displayed formula. We've got all the bonds, all the atoms and the arrangement. So this is a displayed formula that is for pentane. Now the skeletal structure, we get rid of the carbons and the hydrogens and the carbon-hydrogen bonds. We're just left with the carbon-carbon bonds. So 1, 2, 3, 4, 5 carbons indicated by where the carbon-carbon bonds meet. So there is skeletal for pentane. So isomerism, let's take an example. C4H10 can be arranged in more than one way. If I model this, I will then set you a problem in the next slide. Here is what we refer to as a straight chain alkane, so that is butane. But we can also have a branched chain. Pause the video and see if you can draw the branched chain alkane C4H10. Okay, so the branched chain, very simply, we've got, instead of 4 carbons as our longest continuous chain, we've got 3. To go to the 4th carbon, we need to either backtrack or pick the pen up and go to the 4th carbon. So we've got a longest chain of 3 and then a side group. So that would be referred to as a branched chain alkane. How would we write those as structural formulae? Well, butane we've done before today, and here we would represent the branched version. That's methyl propane. So the side group is indicated by the use of a bracket. So carbon, carbon, carbon are the 3 carbons in the chain. The side group is indicated, the CH3 methyl side group is indicated within a bracket. So naming branched chain isomers, I'd like you to pause and try to name the 3 displayed formulae and the 2 skeletal formulae. Try those now. So check your answers against mine. The first one is, of course, 2-methyl propane. I'll just go through how that's achieved. We identify the longest continuous chain. That's 3, so that accounts for the propane. We number 1, 2, 3 in the chain. The side group, methyl group, is on the second carbon, so 2-methyl propane. Propane is this longest continuous chain. The side group has to be positioned 2-methyl propane. Now, if you haven't had that type of thinking on the other examples, pause the video and try. Otherwise, I'm going to, in one moment, share the second answer. So 2-methyl pentane. I'm identifying the longest continuous chain. Not the longest straight chain, the longest continuous chain. So that's 1, 2, 3, 4, 5 carbons. But we're always going to number so that the side group is positioned on the lowest possible number. So that's 1, 2. So methyl pentane, 2-methyl pentane. Moving on to the next one. 2,3-dimethyl butane. How is that achieved? I've got to first of all find the longest continuous chain. So that's of 4. So I use the butane as the naming, as the main name. So that's 4 carbons in a row. So butane. I've got 2 methyl groups. So it's dimethyl. And now I need to position them. So if I number the carbon chain, first carbon, second carbon, third and fourth, then on the second carbon I have a methyl group, and on the third carbon I have a methyl group. There's my 2 methyl groups. So 2,3-dimethyl butane. So 3-ethyl pentane. The key to this is identifying the longest continuous chain. 1, 2, 3, 4, 5 carbons. So that accounts for pentane. That's the main stem. On the third carbon, I've got 2 carbons as my side group. So that would be an ethyl group. So a side group with 2 carbons is an ethane. We say ethyl. So, and then we need to position it. So it's on carbon number 3 of pentane. 1, 2, 3, 4, 5. On the third carbon, we have an ethyl side group, 3-ethyl pentane. And finally, 2,3,4-trimethyl pentane. The key to this is to identify the longest chain, longest continuous chain. Number the carbons. So I've got 5 carbons in that chain, which accounts for pentane as the stem. I've got a methyl group once, twice, 3 times. Once, twice, 3 times. So they're positioned on carbon number 2, carbon number 3, and carbon number 4. So 2, 3, 4, tri-methyl pentane. Trimethyl, 3 methyl groups as side groups. I need to position them. Carbon number 2, carbon number 3, carbon number 4. So 2, 3, 4 trimethyl pentane. So name these alkane isomers of C5H12. Pause the video, come up with the names, check your answers when you're ready. So the first one, 2-methyl butane. Middle one, pentane. No complication there. And the left to right, the third on the right, 2,2-dimethyl propane. I'll just go through that one. We need to identify the longest chain. That's 1 carbon, 2 carbons, 3 carbons, so that counts for the propane. I've got a methyl group and a methyl group, so it's dimethyl. Where are they? They're both on carbon number 2. Both on carbon number 2. So 2,2 2,3-dimethylpropane. So keeping on the same theme, but this time with skeletals, draw skeletal isomers of C6H14. Draw skeletal structures for the isomers of C6H14. Pause the video whilst you do that. Okay, so here are the answers. So obviously our first structural isomer would be hexane, straight chain. Then we're going to take pentane with 5 carbons as the longest continuous chain, and on the second carbon there's a methyl group. So my longest chain here runs like this, and this is my second carbon and a methyl group's on it. Notice I don't start numbering from this end. I number from the end that gives me the lowest possible number in the when positioning the side groups. So I number my carbon chain there 1, 2, 3, 4, 5, and not starting with number 1 down here. Okay. If I started with number 1 down here, this would be carbon 1, 2, 3, 4, 5. This would be 4-methyl pentane. But that would ignore the rule that we use the lowest possible numbering system or pattern. Next isomer would be, well, we can have 2-methyl pentane, then surely we can have 3-methyl pentane. We can now move into the butanes. If I identify my longest continuous chain of 4, so that accounts for the butane, I've got a methyl group and a methyl group, so dimethyl. Where are they? Well, they're on carbon number 2 and number 3, so 2,3-dimethyl butane. And finally, 2,3-dimethyl butane. 2,3-dimethyl butane. Again, identifying the longest chain, there's my butane. Numbering so that I use the lowest numbers in my positioning, in the name. So it's 2, 2, I've got dimethyl, 2 methyl groups, dimethyl, they're both on carbon number 2. So we put 2, we say 2 twice. We write 2 twice. 2, 2. Each methyl group has to be positioned. So 2,2-dimethyl butane. Okay, so to consolidate on skeletal formulae, convert these 2 skeletal formulae into displayed formulae. Pause the video, draw your displayed, and then check your answers against mine. Okay, so when we're drawing skeletal formulae, we don't draw carbons, we don't draw hydrogens, we don't draw carbon-hydrogen bonds. So if I'm going to go to do the 2 displayed formulae, I can add in, if I do this slowly and methodically, I can add in the carbons that have not been drawn in the skeletal, and then I can add in the hydrogens, bearing in mind that every carbon must have 4 bonds. So we need to make the number of bonds for each carbon up to 4 by adding in hydrogen atoms to which they bond. I hope that's neat enough. So I've built up the displayed formulae, and here's a neater version down below. Every carbon has 4 bonds. So if you haven't done the right-hand version correctly, or if you now realize that, pause the video and have another go. So here is the answer to the displayed formula for the right-hand version. As you can see, every carbon has 4 bonds. We've drawn in the carbons, we've drawn in the hydrogens to which they are bonded, and the carbon-hydrogen bond. Check your answer, make sure you can convert a skeletal formula into a displayed formula. Just to summarize on structural isomerism, compounds with the same molecular formula but different structural formulae are structural isomers. For instance, C6H14 on the previous slide, you drew numerous different structures, so those were structural isomers. A little bit more detail tells us that they were carbon chain or skeletal isomers. However, it is possible to have the same molecular formula but have structures that give a different functional group between isomers. And it's also possible to have functional groups in different positions within the same molecular formula. So those would be positional structural isomers. However, the OCR A only really requires you to use the term structural isomer, but you should be aware that there are 3 distinct types of structural isomerism. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers. Move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.